It's a really nice opportunity for me also to visit EPFL, which I've never done before, and especially with this wonderful weather. And on top of everything, today is actually the International Day of Women in Mathematics. So congratulations to all the women mathematicians here, which is another really nice occasion to give this talk. Okay, so what I will do is I will really want to give you a bit of a broad overview of what mathematical imaging is about, what kind of problems we solve, how we solve them, and where I think the exciting developments are happening, where mathematical imaging is taking us. Right, and that is from differential equations to deep learning, roughly speaking. Okay, so let's start broad and then I'll trickle down. So that's the plan. So let's start, since we are mathematicians, let's start with definition. So mathematical imaging is the study and development of mathematical methods for image analysis, image processing, and inverse problems in imaging. And to get us all in the mood for what mathematical imaging can do and what it is about, I thought I'll start by making you watch a video that we shot a couple of years ago with a colleague of mine, Samuli Siltanen, who is an applied mathematician from the University of Helsinki and is really specialized in outreach. So he's doing lots of outreach. He's even on a Finnish science TV show. So anyway, so let me just play the video just to give you a bit of an idea of what we're doing. Okay, I hope this is...
Hey, Carola.
Hi, Samu.
Hey, you know how to remove things from photographs, right?
That's right.
Can we try?
Sure.
Can you make the quote disappear?
Okay. Watch it.
All right, pretty good. I think I can still see something.
Yeah, that was harmonic in painting.
Okay.
We can try total variation in painting.
All right.
Okay.
Oh, pretty cool.
Isn't it?
All right. Can we try some more stuff?
Yeah, that would be fun.
All right.
Let's do it.
Try. That's all pretty cool.
Yeah, that's the power of applied mathematics.
But can in-painting make us disappear?
Sure.
Okay, so I just love to show this video also because it was a lot of fun to actually shoot it. It was yeah, it was very nice. Okay, so let's be a bit more serious now. So I really like to thank my research group in Cambridge. Just a few words about us. They are a great bunch of people who are really behind everything that I'm going to show you. So thank you so much to all of them. And we are based in the math department, so in applied mathematics and theoretical physics, and we develop mathematical methods ranging from differential equations to machine learning. We deal a lot with variational models and also algorithms to solve them, so optimization approaches. To solve a wide range of problems in inverse imaging, in image processing, image analysis. So we do image reconstruction from indirect measurements, such as computed tomography, to image restoration, so denoising, deconvolution, and so on, segmentation and classification, and also the analysis and enhancement of dynamic imaging data, such as motion estimation and object tracking. And we do all of this methods and theory development usually very, very close to applications. So you will see also in my presentation a lot of applications, because this is something I'm very excited about, and I take a lot of my own satisfaction and passion from working on these applications. And again, you can see, because images appear in lots of places, also the applications we are working on are quite diverse. Okay, so what I want to do, as I said at the beginning, I really want to give you kind of a whistle-stop tour through mathematical imaging, and I want to talk about the problems we want to solve, why we want to solve them, how we solve them, and then I'll talk a little bit about perspectives. And I'll end with one thing that we have done if I get there, which if I don't get there, it's also not such an issue, but we'll see. Okay, so what are the problems that we want to solve? Again, starting, zooming out and then zooming in. So the common goal in mathematical imaging is to extract information from large, diverse, and usually corrupted data, imaging data, in an automated and robust way. And so the kind of information that we want to extract varies a lot depending on the problem, depending on the application that we are interested in. Okay, so it could range from, this is a motion estimation example where we have a dynamic microscopy image, and we want to understand where things, we want to quantify where things are going and with which speed. This is an example of multimodal super resolution for hyperpolarized MRI, and this is an example of segmentation, okay, where you want to segment objects and images. So generally, just again, a kind of overview slide of a few kind of prototypical tasks. These are the kind of problems we want to solve, and everything I'm showing you, all the examples I'm showing you for each of these tasks is a bit anecdotal, because I'm showing you the stuff that we have done. Okay, so many people are working on this, just as a disclaimer, but I'm showing you the kind of things that we are doing because I'm quite excited about them. So right, so image denoising is one of the most common tasks in imaging applications, because there is noise everywhere. I mean, noise, imaging data always comes with noise, and so modeling this noise and developing methodologies that can decompose the actual image from the noise is a big topic in mathematical imaging. Segmentation is, of course, another one. So you're not interested in in everything in this image, but you're interested in particular objects. You want to detect and delineate, and then maybe you want to understand them better, so do some further analysis with those. Image reconstruction is another big topic, and this will also be the one that I will mostly revisit, possibly, where a lot of times in imaging, what we are measuring is not an image directly, but it's some indirect measurement. Usually in imaging is some integral transform. Most of the time it's an integral transform. And from these indirect measurements, I want to reconstruct the best image. And so this is usually complicated by the fact that we usually don't measure as much as we need to reconstruct an image. So it's an underdetermined problem. There are many images that equally well fit the same data, and then we have noise. Okay, and in inverse problems, jargon, it's the underlying mathematical issue is that these problems are usually ill-posed. Okay, so this is a big topic. Get the best image out of measurements, basically. And then classification in general. This can be classification of stuff in images or classification of a data set of images into different groups, right? So this is also quite a prototypical problem. So why do we want to do all this? The first application here is actually also a nice story, because it wasn't actually a collaboration that was developed because of college, because of the Cambridge College, where I met a zoologist who was interested in pied flycatcher birds. So pied flycatcher birds are birds which are commuting in the winter, and when they come back, to Cambridge, they breed. Yeah, and so this zoologist had somewhere a couple of breeding boxes where they always came back. And there was this hypothesis that the male pied flycatcher birds, the blaze on the forehead of these pied flycatcher birds, the size is somehow correlated with their reproductiveness. So the kind of undertitle is a little bit like size maybe matters after all. But so what she really, the really kind of simple problem was that she had lots of pictures of these birds. It was quite impressive actually how she did that, because she did that all by herself. So she went to these breeding boxes, she took out the bird, she held the bird in one hand with a ruler, and then she took the photo with the other hand. So yeah, anyway, so that's what we did. We helped her to do this measurement. And there is lots more, right? If you think about the different domains where images come up, so biomedical, the biomedical domain and clinical support is of course a big topic. And so here the problems range from, again, you know, from this image reconstruction task. So you want to get the best images out of measurements, for instance, for positron emission tomography. You might also have additional dimensionality to your data, which you can also use in the context of spatio-temporal imaging, where one really interesting group of methodologies is trying to use dynamics, is trying to use motion to image faster, right? So that somehow the quality of the image that you reconstruct from measurements always relates, or is always dependent on how much you measure, and that can either be related to the radiation dose that you apply. So the more radiation, the better your image, or it can relate to how long you image, for instance, in magnetic resonance tomography. So if you can lower the radiation dose, or if you can reduce the measurement time, this is nice, either because you're interested in the dynamics, or because you don't want to radiate the patient too much, or because you want to make it more comfortable that they don't need to lie in this MRT for a really long time. And so spatio-temporal imaging is quite a big topic also in this image reconstruction business. Related to that is again estimating dynamics, and we have seen a picture of that before. So quantifying motion in images, segmentation and tracking is another one. So here, for instance, we have used this. This is a very early application that we've been working on in Cambridge with people in the Cancer Research Institute in Cambridge, where they were interested in analyzing mitotic cells, comparing the mitotic process between cancer cells and cells that have been treated with kind of chemotherapy drugs, and whether, you know, what the influence of these drugs was. And so this is really a detection and tracking problem and time estimation problem, kind of. Yeah? Another one is segmentation, is of course a big topic in both medical research, but also in clinical support systems for radiologists, for instance. You can really take a lot of effort and time away from radiologists if you can do some automated segmentation. If you can help them with automated segmentation. It really takes otherwise a long time for them to manually do it. And then, of course, in general, diagnostic prognostic tools. finding patterns generally in large data sets. And that can again help clinicians to find connections to patients that have been seen before, and to learn from those, but to make basically algorithm learn, which has a larger capacity to remember everything, and also to make connections between different types of data that have been measured of the patient, and so on and so forth. Okay, so this is biomedical, a few examples. Then another area that we've been working on a lot is conservation and sustainability. So in particular, remote sensing. Here, for instance, this was again one of the first projects that we've been working on in Cambridge, which is delineation of individual trees from LiDAR data. Yeah? And so this, I mean, in this example, it wasn't, this sounds somehow, in this example, if you look at it, it looks rather easy, but if you are looking at very kind of overgrown kind of rainforest type measurements, this becomes quite challenging. Another one, we had this before, classification, so land cover analysis. Here people are interested in understanding basically what our world is made of from satellite imaging data in an automated fashion, and also monitoring land cover over time. So this could be for agriculture, this could be for, again, forest conservation, for instance, where the land cover could be different types of species of trees or plants or something like this. And there is a particular type of imaging that can be used for that, which is hyperspectral imaging, that gives you ideas about the composition of the material that you're imaging from above. Another one that we have been working on for the last 3 years or so is the analysis of video data, either traffic camera videos or Google Street View or something like that, to quantify traffic in cities. Quantify and also stratify. So what type of vehicle are people using? Are they cycling? Are they taking the car? How many buses, trucks are in a city, and so on. And this is interesting for people who work in health modeling, in people who want to basically influence policies for lightening traffic and things like this, for making people, for understanding how healthy people live in certain cities. Yeah, yeah, and then another topic that comes up a lot, and actually all of these different problems, is multimodality. So you usually don't have just LiDAR or just hyperspectral or just video data, but you ideally want to combine all of these different modalities and make quantifications, classifications, make predictions based on a fusion of those. And that has, again, several challenges, which is that you have various different scales. I mean, if you start with satellite imaging and then you're going to go down all the way to having very local measurements with traffic cameras, how would you fuse those? So there is a lot of interesting mathematical questions associated to this. Another topic that is quite close to my heart is that there are lots of opportunities for people in imaging in digital humanities. And so here the idea is that you use image inpainting, which we've seen in the video at the beginning, right? To virtually restore artwork that, in certain cases, like with in this case with illuminated manuscripts, wouldn't been able otherwise. So illuminated manuscripts, I don't know if you know what this means, because the English word was also new to me. These are these manuscripts which have these drawings out of gold and stuff. Yeah. So what monks basically did in cloisters, in the medieval times. Yeah. And so here, these manuscripts are usually very fragile, and so restorers don't touch them. So this the default is that they would never touch them. So virtual restoration is somehow the only way to try to draw, kind of turn the clock backward and get an impression of how things could have looked. And what you see, I don't know if it's very easy to understand when the images are rolling through what it's actually about, but the left one is not even a damage. So what you see here is are damages and stuff, right? But what you see here and also on the top left is actually an overdrawing, where we have used infrared imaging to look through the layers, and then we did something, an image inpainting method that could use both the structure from the infrared and copy back the texture into it from the rest of the manuscript. Wow, that's very fast. Sorry about that. I should have looked at these slides a bit more carefully before. Sorry, but that looks almost like disco. Sorry about that. There are many more applications, right? I should at some point I need to stop talking about applications, but this is well, anyway, limited angle tomography, for instance. So material sciences is a wealth of imaging problems, where one example is limited angle tomography, where the problem is that they can only observe an object from a limited number of directions and have a whole gap of directions missing. And so it's a kind of in-painting problem, but in this projection domain, right? In this measurement domain, where I've said before, there are lots of problems in imaging where you don't measure an image directly. In this case, it's a projection domain. Another nice area that we worked on now for maybe 7-8 years is computational fluid dynamics, where we met a group in chemical engineering, where the PI always said, I worked on bubbly flows now for all my career, bubbly flows, but basically she's interested in dynamics of gas and fluid together. So here what you can see is like a tracer injected into a tube, and they use MRI, velocity encoded MRI, to actually quantify that. Zoology we already saw, and something that we started recently is in molecular biology. There's also a lot of interesting mathematical problems associated to molecular biology, in particular in the context of what is called cryo-EM, single particle imaging, where again they use electron tomography or electron microscopy to image molecules. Also very super small. Okay, so these are the applications, and I could talk more about each of these, but I won't. Now, how do we solve these? What are the approaches that people have been developing? And so for thinking about how to solve these different problems, it's maybe good to spend a few minutes on understanding what the challenges are when we deal with imaging data. And I appreciate most of you are dealing with imaging data, because otherwise you wouldn't be here. But just to be on the same page, let's maybe remember this again together. So I'm stealing here something that IBM has used for characterizing big data, but I think it equally applies for imaging data. So the 4 V's. The 4 V's are, and this is something that our methodologies need to take into account, right? These 4 V's, which is volume. Imaging data is usually huge. It's high dimensional, it's large. And if you go beyond, image processing papers, which look at some benchmarking image data sets that are of relatively modest size, if you go to real imaging data, this becomes a real challenge. Variety. So again, just thinking back at all the applications that we've been discussing, images can come in various shapes and forms, right? And so the moment you think about algorithms that somehow do something automatic with images, that detect certain patterns and make use of these patterns to solve image tasks, they need to be able to characterize structures in images that we are interested in. And that in such a generality could be quite challenging, because of images looking very different, right? Depending on what application you're looking at. Velocity is the other one, and that's true for all kinds of data, right? Not just for imaging data, but data in general is now acquired at increasing speeds, and so also our methodologies need to react to that and be as fast as this, I guess. And the other one is veracity, which is noise and corruptions that we have in the data. And so in general, what we measure is complex, diverse, large, messy, and also the information in it, in particular, if you're thinking about you really using imaging in the real world, can vary tremendously and also often unpredictably. Think about using imaging for scientific exploration. We don't know what is happening. That's why we use imaging. And so the requirements on the methodologies that we develop, therefore, need to fulfill certain criteria. They need to be robust to the corruption. They need to be able to handle unseen data. They need to be sufficiently accurate to be able to be rolled out in a, let's say, clinical setting, for instance. And they need to be computationally affordable and in particular scalable. Yeah? And so in the last, I would say, maybe 5 to 10 years or so, the kind of approaches of how people have been thinking about solving these image processing tasks have really kind of crystallized into two main paradigms. So I think, you know, when I grew up as a PhD student, I have been only working on one of these paradigms. This is where I'm coming from. I'm, you know, someone who has been working on partial differential equations and variational models for half of my career to date. And then all of a sudden, deep neural networks came around and showed a lot of impressive results. And I think the community now also has kind of been reacting to that, that people in mathematical imaging, you know, think about approaches in these two categories. So one is the knowledge-driven approach, where we look at a problem we want to solve. We try to mathematically formalize a solution to this problem in terms of a differential equation or a variational model. What is used a lot in these mathematical models is the fact that the information we want to extract from images, or, you know, images themselves, can be represented in a sparse way in some kind of dictionary, in some kind of expansion. So this is really a main assumption that has been very successful and is very successful, but has its limits, as we will see in a moment. Okay. And then the other idea is you basically get models from data. Okay. So you start with a super generic model, for instance, and this is really kind of the prototype nowadays would be a neural network. And you have a lot of examples of the kind of information about the kind of solutions you want to get from a task, from an image task. And you use those examples to train, to find an appropriate model for your task. Okay, so this is somehow the idea. This is data-driven versus knowledge-driven. Now, quickly, let's just appreciate what these different approaches have and what they don't have. Yeah? So in the one example of a knowledge-driven paradigm that has been extremely successful is variational models, variational regularization. And that really comes from inverse problems where variational regularization has been introduced to counterfight the ill-postness of these problems. Here, just for simplicity, I write it down for image denoising. The idea of variational regularization is, okay, I'm measuring a noisy image, okay, and I'm interested to extract the clean image from the noisy measurements, where n is just a placeholder for generic additive noise in this case, okay? So the variational regularization approach casts this problem as a minimization problem, where I'm computing an approximation to my clean image as a minimizer of a functional that consists of two tasks, of two terms usually. One is my data fidelity or data discrepancy term, and just look here, this is the most, I would say maybe 90% of the time, this is least squares fit to the noisy image. Okay, and this is complemented with a term that should basically attenuate the noise, that should get rid of the noise in the image, that acts as a regularization, as a smoothing, and that is weighted against fitting the clean image to the noisy image with the regularization parameter alpha. Okay, and the prototypical regularization that has been extremely prominent and successful in mathematical imaging is the total variation, which is a sparsity promoting regularization that basically says, again, going back to this sparsity assumption, right? That says, I'm assuming that the clean image I'm looking for can be best described by its edges, by its discontinuities, and some constant intensities in between, okay? So it's a kind of piecewise constant approximation to the clean image. And while if you think about images, this might not be true for everything, right? Actually, not true for almost everything. It's a good proxy, in particular in the context of kind of medical or scientific imaging, where we are not looking for pretty images, but we are looking for images with which we can quantify things, right? And for quantification on the basis of images, edges are actually quite important. And this is what the total variation exploits. So just as an example, to give you an impression, probably many of you have seen total variation regularization with Michael around here. So, but still briefly, let me show you. So this is denoising, a simulated example. This is the original. This is a noisy image, just white noise, white Gaussian noise. And here are two solutions of this variation regularization approach. One with the H1 with an H1 semi-norm regularization, which is the typical regularization, this Tikhonov regularization that people have been using in inverse problems. And this is the total variation. You can see immediately the difference in that the total variation is really kind of bringing out the edges and really making a difference between smoothing the more homogeneous background versus preserving the main areas where the gradient is large. And it does that just conceptually, again, if you don't know about the total variation, it does that by quantifying the amount of oscillation that you have in your noisy image and tries to attenuate that. Okay, so and because noise is small oscillations, that's why this works, very roughly speaking. Now, also differential equations have been mentioned a lot already, and I haven't shown you differential equations really. So the differential equation can be actually easily derived from, again, looking back at the total variation regularization problem for image denoising, which is also called the Roth model for Ruden, Osher, and Fatemi, who have been the ones who popularized this a lot. And because again, just very briefly, because so a partial differential equation arises as a gradient flow of this minimization problem. So basically, think about when you want to solve a minimization problem, one thing you could do is gradient descent, right? If you write down gradient descent for this functional, you get you get actually a subgradient flow, okay? But if you don't, because it's not differentiable, but if you're not into this, let's just say what you get if you're looking at the areas where you can actually differentiate the total variation, then what you get is a highly nonlinear diffusion equation, which if you start, and this is what I'm doing here, right? I'm starting this evolution equation at time t equals 0 with the noisy image, and then I just evolve it along this equation where I've chosen the alpha very large, just to show you what the smoothing process looks like. Yeah? And so when you look at this nonlinear diffusion term here, again, what you can see what this total variation regularization, what the smoothing process is all about. Yeah, it's really, if you think about it, what this is weighting the diffusion with 1 over the modulus of the gradient of u, which means that if the gradient of u, which is somehow telling us how sharp my edges are, right? In the image, if this is very large, I will diffuse less. If the gradient of u is small in kind of homogeneous areas, I diffuse more and I can get rid more of the noise. Okay. So, okay. So the nice thing about this are kind of prototypes of this knowledge-driven approach to imaging. And the nice thing about this knowledge-driven paradigm is that this gave a lot of interesting food to mathematicians, in particular applied analysts and also numerical analysts, who could, on the one hand, make sure that these models are actually doing what they are supposed to do. They are stable, they are robust, they have solutions, but then also to derive qualitative properties of solutions of these equations, so we can actually kind of explain and understand what the solutions are made of. And then, because on the numerical side, these problems are usually on the tougher end of the spectrum, because they are non-smooth optimization problems and because they are nonlinear PDEs that we need to solve. They also triggered a lot of interesting development on the computational side. Yeah? But basically, the message of this slide is that we have them more or less under control, yeah? And we understand what they are doing. And sorry, did you want to take a picture of this? And I'm not at all, by the way, complete, but this is just a few things that came to mind here. And then also the total variation is not the only regularization that people have been developing, that people have been analyzing and using, but there is a whole zoo of different approaches, of different types of nonlinear PDEs, of different types of variational approaches that have been around. Yeah, and then of course, and I've mentioned this briefly, you can go beyond denoising. Yeah, you can formulate this for various image processing inverse problems tasks by just putting here a linear operator in between the measurements and the image. Okay, so I'll be brief here, but this is the idea. For instance, you can do image inpainting. Yeah, so this is when you choose as your operator T here a projection onto the domain of the image that is known, right? Then you can use the regularization as an interpolation, as something that interpolates from the known area into the unknown domain. And that's just an example, which nicely leads me to the data-driven paradigm, where, so, okay, knowledge-driven paradigm, we have seen what we can do, blah, blah, blah. But if you go back to this image inpainting, right? So mostly when variational regularization people talk about image inpainting, you mostly see examples like this, where you have small areas that you want to interpolate. And sometimes this could be even quite impressive, because people say, I take 80% of the pixels away, just randomly select pixels that I leave out, and then I interpolate. And this usually works well. Yeah? But the moment you have large areas, let's say you cut out the whole eye of this fish, this kind of total variation regularization wouldn't be able to reproduce the eye, right? Makes sense somehow. Yeah? And this is, I think, where this data-driven approaches, I think this shows really a significant step that data-driven approaches have allowed us to do. Yeah? So yeah, I mean, just, and this is even, you know, this is a couple of years old, so it is not even the state of the art, but when you appreciate that these knowledge-driven approaches would have a very hard time in doing something like this. Yeah? So on the other hand, and they really do this by not writing down a mathematical equation that should interpolate, you know, Einstein's wrinkles or something like this, but they do this by seeing a lot of examples by learning from the data, by deriving in particular. So again, thinking back to this data-driven paradigm, deriving models from data. Okay, and this is very powerful, but it's also something that comes with challenges, right? Because while before with the knowledge-driven approaches, we had all these nice explanations, we could analyze solutions, and so on and so forth. With deep learning in particular, the deep learning that is used in practice, yeah, so the messy deep learning is used in practice with deep networks and so on, is mathematically not understood at the moment. Yeah, and so in particular, this is, you know, this hits practitioners even as well, because there is no real systematic way to design them. There is a safety danger, and I will not go into this because I'm sure you have heard this many, many times. And there is, of course, a lack of interpretation. And there are, you know, things that are happening on the mathematical side, but it takes time. And the question is if they will ever solve everything we want to know. So if we systematically now think about, so this leads me into the challenges. If we systematically think about the pluses and minuses, the advantages and disadvantages of knowledge and data-driven approaches, then we could come up with a table like this. Huh? And so I want to briefly now just collect our thoughts before I tell you what I think, and you'll already might predict where I'm heading, where I think the domain, the mathematical imaging domain is going. So reflecting again a bit on the knowledge-driven paradigm, and mainly discussing the negative features, is of course they are limited in terms of how much they can adapt to the data. This is just how they are made of, right? This is also their power because they generalize super well. Again, think about total variation. Edges are everywhere, but of course, images are not just made out of edges. So this is the kind of conundrum between generalizability and also limited adaptivity to the data. But you can see, and this is one example of variational regularization reconstruction. This is again total variation regularization for computer tomography reconstruction from sparse few data. Okay, so you don't measure all the angles, but you leave out a couple of them, but kind of distributed. Okay, and you have noise and stuff, so you can reconstruct with TV something like this. But if you go to one of the latest deep learning type of approaches, you can reconstruct images that look like this, yeah, which I think you can clearly see that there is a huge step that you do in terms of detail that we can see in these images. And the reason why we can do this step is really because what is exploited in these type of approaches is that they have seen, in this case, maybe high dose, fully sampled CT images before. The other thing is, negative side is of these knowledge-driven approaches is that they are computationally really demanding, right? I've mentioned this before, nonlinear PDEs, non-smooth minimization problems, sometimes even non-convex ones, actually also increasingly often non-convex minimization problems. So these are computationally very tough, and then again we have large data that we need to process with them. So that is something that is definitely a negative. And again, if you think about, for instance, the data-driven paradigm, deep neural networks, they are very expensive to train, but once they're trained, they're an explicit application of nonlinear and linear operations. And while this can still be costly, right, doing large matrix multiplications and stuff like this, it's quite different to doing some implicit, you know, some matrix solvers and stuff like this, like here. Okay, so what about data-driven? So what are the negative sides here? I mean, one definitely is with the adaptivity to the data, what comes with it is also that they are not as generalizable to new, to out of distribution samples, let's say. And that means we usually in imaging need a lot of images to train with, in particular for the fully data-driven approaches. the other negative side is this black box character. Okay, so this black box character is not just intellectually unsatisfying, but it's really an issue because bad things happen, basically, and in particular in problems which are mathematically very tough to solve. So this is again computer tomography, an example of computer tomography. But going back to this disco video I've shown you, yeah, this is the limited angle problem. So where you really have a whole range of angles missing. And this is mathematically extremely ill-posed. So it's a very, very tough problem to solve. Now, if you do this with, I call this here handcrafted, in this case, it's just filtered, what is called filtered back projection, you get something like this, and you see exactly where the angles are missing. Yeah. So by the way, all of this is simulated, which is why I have the ground truth. Okay. Just to tell you. So this is just an academic example, so we can see what we are aiming for. Okay. This is what you get again with a state-of-the-art learned approach. And so if you look very quickly, maybe you think, oh, wow, that's amazing, that's great. But if you look a bit more carefully, you see it's not great at all. Huh? Look, for instance, just at the shape of the whole thing, right? This is not at all the shape of this patient that we have imaged, right? This looks super strange, has a kind of strange thing here. If you look at, I think the easiest to see is that it's really off. It's not consistent with the data that we have measured. Is if you look at the bone structures, these are also, you know, even in the part that we should see, right? This is even the part where we should have some information. It's completely messing this up. Yeah, so I can see this is already starting some discussion. Yeah, but this. Yeah, and this is not just a plain vanilla deep learning approach that has produced this. This is one of these learned iterative reconstruction schemes called learned primal dual that has produced this. So this is just, we need to be careful. Okay. Okay. So, and I think, and this is where the perspectives start, and I need to stop soon. So, but I'll briefly show you something. I think where the power of mathematical imaging and the really exciting developments at the moment happen is exactly at this interface between data-driven and knowledge-driven approaches. And I'm almost sure that many of you feel the same, and many of you think in a similar fashion, but I think the idea really should be that we use the data-driven approaches where we need them and use the models, the mathematical models, as much as we can. Huh? And yeah, and then you can do, hopefully at some point, end up with a table where we combine the best from both worlds. So this is somehow the idea. Sorry, I had some nice quotes here, but I'll just continue because I want to show you one example. Yeah. So one example for that is in the context of image reconstruction. So this tomographic image reconstruction, which we have seen before. And here deep learning has had a huge rouse of new approaches that have been developed in the last years. And I just want to show you one because we have talked about variational regularization a lot. And because one of the ideas that we have been working on is to basically stick to variational regularization, but replace the regularizer, so the smoothing procedure, basically, by a neural network. So this is all that is to it. Okay. So this is one way how to combine it. And the idea of combining it in that way really is to plug in the neural network exactly where we need it, namely in the regularization, the smoothing term, which is the hardest one to model. Yeah. Because of what is here in the slide. Okay. Because of the fact that images are very hard to model. So this is joint work. We have been working on this for the last 5 years or so. So this is joint work with many people on and off. The main person who started this is Sebastian Lunz, who has been a PhD student of mine. And now the main person working on this is Shubha Mukherjee, who is actually just been hired by Bath, but is at the moment still in my group. Okay, so very quickly, I know I should stop, but I just want to show you the idea, okay, so of how you could do something like this. So this is the variation regularization approach. We just go back to what we've seen before. And now what I'm telling you is I want to stick to this for image reconstruction, okay, for tomographic image reconstruction, for instance, but I want to now make this regularizer data-driven. And so if you want to make it data-driven, you basically need to first think about how would you train a regularizer that would fit into such a variational approach, right? And how you would train it is exactly conceptually in the way of what the regularizer's role is in the variational problem. Namely, what you want is that the regularizer penalizes the reconstruction that you don't want, and it should favor the reconstructions that you want, while these reconstructions should still fit the data, right? And this is exactly how we train it. So we create a data set of what we call the good guys. So this could be in a CT context, high dose CT reconstructions, and the bad guys, which are reconstructions that we produce from the actual, let's say sparse view CT measurements with our baseline method, which could, for instance, be filtered back projection. Okay. And then we train the regularizer in the spirit of how you train a discriminator for a generative adversarial network to, on the one hand, favor the good guys and penalize the bad guys. Okay, so this is the idea, and I'll not bore you with this here, but yeah, basically the idea is we train the regularizer as the discriminator in a generative adversarial network framework. Okay, so this is basically the idea, and then we use the trained regularizer, we plug it back into the variational model, and then we solve things. And this works, and we have seen this before, so I will not show you actually the reconstruction I've shown you before is with this, what we call adversarial regularizer, because it's kind of trained in this adversarial fashion, okay? And that, reflecting back on the table that we desire to get is partially, so there is no red stuff anymore, which is good. Partially things are black because we don't know. Generalizability, we just have empirical observations that are promising, but I don't know how generalizable this regularizer really is. And then inside, of course, while we can get some reconstruction guarantees for free from all this wonderful theory that I've shown you when we talked about the knowledge-driven approaches, it's hard to interpret a neural network regularizer. And then otherwise we're kind of happy, but yeah, these are the things. So let me finish on that note, and then I'll stop. I think with all of these approaches, and now in particular hinting towards deep learning for image reconstruction, I think what is missing at the moment is to really work out a use case, a really convincing use case where this can make a difference, right? Because again, in a way, we don't reconstruct these CT images because we think they look pretty, right? Or we want them to look pretty. We want to reconstruct them because a radiologist can then do, let's say, some radiomics on them and get more accurate features out of these images that can then help the radiologist to make treatment plans for patients, to make predictions of how the cancer is evolving and things like that, right? And I think these kind of use cases are still missing. And I think one really cool direction, or one really cool development that is happening, are these scanners, these MR or CT scanners that are kind of bedside scanners. So which have really crappy measurements, right? So you have really, really, let's say, low dose measurements. This is where I think where these type of approaches could make a huge difference. If you could still get some a little bit more information out of these machines. Okay, so on that, I think I'll finish. I need to finish. We have the apéro. So the message for me really is hybrid methods, the combination between the two paradigms. Knowledge, data-driven paradigm is really the future, and there are lots of really, really interesting opportunities to do research, both on the theoretical side, on the methodological side, and also on the applied side that will come with that. So I think it's a really exciting time to be working in this area. I thank you very much for your attention, and again, happy International Women in Mathematics Day.